So good morning, Advanced Chemistry. We're going to start with some notes where we left off on Friday, talking some more about solvation, specifically why things will be either soluble or insoluble in water. And all nonpolar compounds are insoluble in water, and we want to talk about why that is. So we've got this rule called like dissolves like, and I want us to dig into that a little bit more and talk about why we have that rule. But first, let's write down the rule. The like dissolves like rule applies to polarity. So if you have a polar solute, that is going to dissolve in a polar solvent. Similarly, if you have a nonpolar solute, that's going to dissolve in a nonpolar solvent. And actually, we can make this a little bit more thorough by noting that if it's polar or if it's ionic, then those things will most likely dissolve in a polar solvent. They're not going to always, so most likely. So just because it's ionic doesn't mean it's always going to dissolve, but if it's going to dissolve in something, it's going to be a polar solvent. Same thing for nonpolar. Doesn't mean it's got to dissolve, it means it's most likely to dissolve. Okay? Also, if you have a nonpolar solute, that will not dissolve in a polar solvent, as well as vice versa. A polar solute will not dissolve in a nonpolar solvent. Should add that in there. It got cut off, it looks like. Nonpolar solvent. So that's our like dissolves like, or non-like does not dissolve in non-like rule, however you want to think of it. And I would like to discuss why that is, but before that happens, I would like to show you a quick video of what that looks like in real life. So here we go. This is something, a little treat I found on YouTube. Okay, now what you've got here is two different cylinders, each full of 3 different liquids. So you can see the 3 layers there as the camera pans up, and it's going to identify those layers to you. So it says the 3 layers in each cylinder. Chloroform, which is nonpolar, water, which is polar, and ethyl acetate, which is nonpolar. So I'm going to just write those in there quickly. So ethyl acetate is nonpolar, water is polar, we know that, and chloroform is nonpolar. And then we've got these 2 compounds down here, iodine, which is I2, which is completely nonpolar, and copper 2 sulfate, which is ionic. And you guys can think of ionic as like super polar. It's like so polar that it has complete charges. Okay, so what we should predict, or what we should see happen here, is that our ionic copper 2 sulfate should dissolve only in the water. So copper 2 sulfate should dissolve in the water, but not in the chloroform or the ethyl acetate. And the iodine should dissolve in the chloroform and the ethyl acetate, but not in the water. So it's kind of cool to see this happen. So I want you to see it. And I'm going to be quiet and let you just watch. Turn up the volume here so you can hear it. Okay. Great soundtrack. So here we go. Adding the solutes. Now they're going to go ahead and switch solutes. So let's apply some dissociation principles based on what we've learned so far. First, let's talk about a soluble ionic compound. By the way, the easiest way to know if something is soluble and an ionic compound is to check your solubility chart, which I have extra copies of this morning if you need that. But remember, on the solubility chart, something that's going to be soluble in water is going to have that designation of S. So you kind of play battleship on that chart. For example, if it's copper 2 sulfate, you find your cupric or your copper 2, and you find your sulfate, you bring them together, and you should see an S. That means that it's soluble in water. So if you have a soluble ionic compound, let's take this beaker here and apply what that would look like in solution. We talked about this a little bit on Friday. So let's take, for example, let's do sodium. And one thing you can notice about your solubility chart is that all sodium compounds are soluble in water. So let's do sodium oxide, Na2O. And we are going to show our sodium oxide. I'm going to have you draw them. So sodium, Na2, let's make sodium purple. So we're going to have 2 of those. And we will make our oxygen, let's make it orange. And we're going to make that a rectangle. So there's our compound as a solid, or in solid form, where our ionic bonds are present and are keeping our positive sodiums attracted to our negative oxygen. When I put this into water in this beaker, so we're going to pretend that this beaker is full of water, so I'll make it pretty blue. I want us to draw a picture of what would happen. So in it goes. And if this is a soluble ionic compound, it is going to dissociate. So in solution, what we're going to draw is all of those ions separated from each other. So we'll have 2 sodiums, and they'll be separated from each other. And then we will also have our oxygen ion. That's a -2. And that will be separated. And then these will all be surrounded by the sphere of hydration. So I'm going to draw that in kind of like this, the sphere of hydration. Because those will all be in that cloak of invisibility in the sphere of hydration. Now remember, for the Na+1s here, we're going to have, if I were to zoom in, the Na+ would be surrounded by, on the water side, since it's the plus for the sodium, the oxygen part of the water would be facing, the sort of negative would be facing the sodium's plus. And then obviously backwards, so the hydrogen sort of positives would be facing the oxygens here, but they would all have that sphere of hydration. So the little cloud there is our sphere of hydration. Sphere of hydration. Because they dissolve. Okay, so how we would write this out, and again we were talking about this a little bit on Friday, is if we were to dump this into H2O, we would have 2 Na+1, and that would be aqueous, and we would have just the 1 oxygen -2, which would also be aqueous. So you can see we have a simple binary ionic compound there. Let's talk about some others. How about a insoluble ionic compound? Oh, sorry, soluble ionic compound with a polyatomic ion. So something like what was in your quiz today. So how about we do what was in your quiz today, which was Na2SO4, which would be a solid as an ionic compound. We'll go ahead and use purple for our sodium again. So I'm going to draw 2 purple sodiums. And then we've got our SO4. So I'm going to use, let's see, I'll use orange again for my oxygen. And I've got 4 of those. 1, 2, 3, and 4. And we'll make our sulfur red. And we will make that a squiggle. Okay, so this whole thing over here, this whole polyatomic ion, I'm going to draw a line around because that guy right there is going to stay together. So that has covalent bonds inside because an S to O difference in electronegativity is going to be very low. So all of those bonds inside are going to be covalent bonds, which are much more difficult to break. And remember, in order for something to dissolve or to dissociate, the attraction for the solvent has to be greater than the attraction to itself. And those covalent bonds are very much attracted to themselves. These bonds, however, those ionic bonds, so those are ionic, are much easier for water to get in and break. So if this goes into our water, again, I'll make this look like it's water here. If this goes into water, and we did talk about this a little bit on Friday too, then what we're going to see is the sodiums dissociate one from the other, and they are also going to dissociate from this entire black box full of stuff. So we're going to have the whole black box as one unit all together, and inside of there is going to still be our 4 rectangles and our squiggly representing our sulfur. So that's going to stay together, but those are going to dissociate from each other, and all 3 of those, since this is soluble, all 3 of those are going to be surrounded by their own sphere of hydration. And so again, and I didn't talk about this on the last one, but because we have 1, 2, 3 ions in solution, our Van Hoff factor is going to be 3 for this. It's also going to be electrolytic because it can conduct electricity with those free-flowing ions. So what this would look like, if I were to write out this process here, would be, and this was on your quiz as well, I would have 2 Na+1s separated from each other, both aqueous, that is the sphere of hydration there, and the SO4 ion, the sulfate ion with a -2 charge, but that's going to stay all together because of the covalent bonds that make it up. So that I value is going to be 3, and it's going to be electrolytic because it's able to conduct electricity with the free-flowing ions. Our last example, the Na2O, that also would have had an I value of 3 because you had 2 NAs and an oxygen, so 3 ions altogether. Alrighty, moving on here. Let's talk about an insoluble ionic compound. So something like, again, on your solubility chart, you might have something like copper hydroxide. Now, if it's insoluble and it's ionic, that means it's not going to dissociate. So how about will not dissociate? So if it's insoluble and it's ionic, it's not going to dissociate. So this is a very simple process to draw. If I make my copper, I want to make my copper blue because most copper compounds of the +2 variety are blue. And then the OH2, let's make our oxygen orange again and our square. And let's make our H's green. And we'll make those stars. There's an OH and there's an OH. And I'll go ahead and box those in because those are both polyatomic ions, so those have covalent bonds holding them together. Okay, so we would have ionic bonds from the copper, which is +2, to each of the hydroxides, which are -1. However, when that goes into solution, it's not going to dissociate. So in other words, nothing really happens. This is not going to dissolve. So it's going to sit there like a exact replica of what it is like outside of solution. And since it doesn't dissolve, there will be no sphere of hydration either. So I'm just going to draw our two boxes here. And it will not change. So inside we'll still have the orange oxygens. And we'll still have our green hydrogens, and they'll still be stuck together. But these two pieces now, the ionic bonds, will not break either, will not dissociate. So no sphere of hydration and no dissociation. So this would be considered a non-electrolytic solution because you have no free-flowing ions based on the fact that it did not dissociate. There's no free-flowing ions in solution, so the solution cannot conduct electricity. Okay. If we have water as our solvent and we have a polar molecular compound, so let's take, for example, a compound like methanol, which is this guy right here. He's got OH. Okay, so this is a polar molecular compound. If it's polar and molecular, it will probably also be soluble because like dissolves like. So because of the fact that this molecule is polar, it is most likely going to be soluble. Now that's not always the case, but for now, we're going to go with it. So if this thing is soluble, because it is polar, and because it is molecular, this means it is not going to dissociate because it is not made up of ions. So no dissociation because you have all covalent bonds. So something with covalent bonds is not going to dissociate, just like those covalent bonds within the polyatomic ion. So that didn't dissociate. So something that is completely made up of covalent bonds is also not going to dissociate. So if this is soluble, which we said it was right here, if this is soluble, now I'm going to draw this whole thing as going in here. So I have C, H, H, OH, and H. Now that whole thing is going to stick together. But since it's soluble, I am also going to draw its sphere of hydration. So because it is soluble, it gets that sphere of hydration. So anything that is dissolved in the water has to be inside that sphere, that cloak of invisibility. Now in this case, that sphere of hydration has a lot bigger area to cover because instead of an individual monatomic ion or even a polyatomic ion, we've got an entire molecule. There's a polar molecular. Okay, assuming it's soluble. If we have a nonpolar molecular, now remember, like dissolve like rule tells us that a nonpolar is probably going to be insoluble. So let's take, for example, let's do butane. And butane is a 4-carbon molecule with all carbon-hydrogen or carbon-carbon bonds, which makes it completely nonpolar. We're going to talk a lot more about these carbon compounds later in the year. But for right now, you can see we have this big molecule, and it's got all nonpolar covalent bonds. So we know with the like dissolves like rule that since it is nonpolar, it's not going to dissolve, or it's most likely not going to dissolve. So we put it in there, and basically it should look exactly the same as what it does outside of water, except for now it's in water. It's not going to have a sphere of hydration because it's not soluble. So basically, it's just going to all stay together because it's covalent, and it's not going to have a sphere of hydration because it's not soluble. So here's a quick check, and I'm going to pause this after I put it up on the screen, but I want you to see how you do on these three. I want you to draw what each of the following would look like when dumped into this beaker of water. So I want you to try formaldehyde, and I'm going to give you the formula for formaldehyde here in a second. I want you to try sodium carbonate, which you should be able to get the formula of yourself. And then I want you to, because we didn't really talk about this much after the first couple, which one of these or both or neither would conduct electricity or be electrolytic. So I'm going to pause this for a second, or ask for your sub to pause this for a second. Have you try those two, and then we will talk about it together. Sorry, I forgot to tell you what formaldehyde is. Formaldehyde's Lewis structure, hint, hint, wink, wink, nudge, nudge, looks like this. Okay. So that should help. There you go. Okay, so let's start with formaldehyde. Formaldehyde is covalent, and I wanted you to try to see if it was polar or nonpolar before you started so you could see if it would dissolve. So the carbon to hydrogen bond is nonpolar, but the carbon to oxygen bond is polar. And the electrons would move this way, and that's because oxygen has an electronegativity of about 3.5, and carbon's is about 2.2, and so that's a difference of, oh, I'm sorry, that is wrong. Oh, I guess that's pretty close. So you've got that big enough difference there where this is going to be polar. So anyways, since it's polar, it should dissolve. But since it's covalent, it should not dissociate. So what this is going to look like in here is the intact molecule enclosed by a sphere of hydration. So intact because it's covalent and it won't dissociate, but a sphere of hydration because it's polar and it should be soluble. So that takes care of our formaldehyde. Now for our sodium carbonate, and you can see I have that drawn here, I chose to use purple again for sodium and my little dotted lines here to show that there are two ionic bonds. And then the carbonate, whoopsie, the carbonate there, represented by this box here with the 3 oxygens in orange and the carbon then with like this lightning zigzag thing going on. So, if I dump that guy in there, then the ionic bonds should dissociate, because if you look at your solubility chart, sodium carbonate, like all sodium compounds, is soluble. So what's going to happen here is that the ionic bonds will dissociate, meaning you're going to have two sodiums dissociated from that carbonate ion, which is the whole box. And I'm not going to spend the time to draw everything in that box, but it should be the lightning bolt and then the 3 oxygens there. And since it is also soluble, it's going to dissociate as it's ionic, and then everything should also be in the sphere of hydration because it's soluble. Now the I value here would be 1, 2, 3 again. And because I have free-flowing ions here, it would be electrolytic. However, in formaldehyde, there were no free-flowing ions, so that would be electrolytic. So would one or both or neither, just B would be electrolytic because it has the free-flowing ions. Okay, so I'm going to have you guys practice with that some today. And in the practice problems 1.2, there's just a lot of this. Some is just writing the equations out, and some it's drawing. And feel free to use some of the markers there. I should have put markers out at all of your tables if you would like to do that, and then we'll discuss it tomorrow. So thanks for your attention, and have a lovely day, and I will look forward to seeing you tomorrow. Thanks, guys.